Hi, my name is Louis Vest, President and Project Lead at Titan Rover. Titan Rover acts as both an educational club and URC design team. The design team sets out to design and manufacture a complete rover for URC. Previously, our team developed Calypso, creating iterative design changes based off former competition platforms. This year, Titan Rover's design team elected to further improve rover functionality, identifying key systems based on testing and past URC performances, allowing for further iterative design changes to the rover's core systems. I am proud to present to you Odyssey, based on the Calypso platform.
The mechanical team primarily focused on analyzing the strength and identifying areas of failures of components using FEA software. From this data, we were able to determine key areas in all subsystems that demanded redesign, weight reduction of the system, and an increase in the overall performance of the platform.
Odyssey's mobility system consists of a double wishbone pneumatic suspension powered by dual DC motors. The Rover traverses on large 18-inch wheels that provide an exceptional ride height and wide wheelbase to enhance traversal over hazardous terrain and minor obstacles.
Odyssey features a 5-degree of freedom robotic arm whose carbon fiber limbs act as structural members and internal channels for all wiring and control systems. The arm contains an external belt truss system, granting improved serviceability and an overall reduction in weight. Each joint is modularly designed to facilitate system integration and contains feedback, enabling real-time position tracking from the base station.
This year, for our soil extraction, we're using a solid stem auger constructed out of a high-strength nylon polymer. The auger will probe each test site and transport the soil to our distribution chamber. A controlled volume of soil will then enter its respected test beaker for further scientific analysis.
The rover will characterize the soil samples through 4 distinct tests: a UV sensor to classify microorganisms found at each site, a test for organic compounds to compare the various sites' potential for harboring life, along with a chemical extraction process to quantify the presence of peptide bonds, and a microscope to search for single-celled and multicellular organisms while exploiting the possibility of convergent evolutionary traits developed both between organisms at the Mars-like environment and on Earth.
By giving the science team specific operation of the science system, separate from the rover drivers, we increased our ability to simultaneously control both systems. Building a separate interface for the science team simplified the required user experience and optimized background data processing and data interpretation for this task.
Our team has managed to implement numerous printed circuit boards, each equipped to handle environmental conditions and traversal. With the help of one of our sponsors, Altium, we have been able to design voltage regulators, Ethernet switches, also a power and signal distribution board which will get connected onto our onboard computer to centralize all of our sensors and drivers into one system.
All functionality for the rover has been developed in the ROS environment using Python and C++ programming languages. We have created a multi-ROS core system, allowing the rover to have independent functionality without the dependence of the base station operations. With this independence, the operating environment has become standardized, enabling multiple points of access control, from direct joystick to autonomous navigation to our own mobile application, and even multiple driver control from the base station.
This year, all necessary onboard processes on TX2 communicates to a centralized ROS server to retrieve data and publish custom messages consisting of movement commands and sensor data. The system also keeps track and periodically updates the GPS stack to recover from unexpected communication loss by returning back to the prior GPS point until the communication is restored. The autonomous system retrieves centimeter-accurate GNSS position along with IMU heading to proceed towards target using SLAM navigation integration.
We've adapted our base station to run task-specific UI applications. We've built a graphic user interface with industry-recognized frameworks. With these frameworks, we have seamlessly integrated ROS with our UI and plugins, which create a central running environment. Embedding configurable and optimized video feeds within the UI reduces network traffic and information delays.
The navigation system provides object avoidance running a SLAM environment based on dead reckoning design. Using a solid-state LiDAR, the rover analyzes a 3D point cloud of distance data and creates a geographical map to optimize the navigation system. The IMU adds additional sensor data to increase the accuracy of the geographical map.
For tennis ball recognition, we have used region-based convolutional neural network. We are using a rotating camera to provide a 270-degree scanning area while navigating along a spiral search pattern to locate the tennis ball. GPS coordinates of the ball are calculated based on the ball's size and location offset within the image.
With past URC experience in development, Titan Rover stands ready with a fully refined, robust robotic platform. Thanks, and I'll see you in Utah.